So that last time we already go to this particular session, right, about air conditioning system. So that again, so it's one of important topic for building or the modern building. Let me quickly show you this kind of video again. This is a very simple, right, animation to tell you how the typical air conditioning work. There's a 4 key component, right? And the goal is clear. This thing is try to pump, right? Pump the warm air inside this machine, and then try to do some what? What's the goal? Heat exchange, heat transfer, right? And then let the kind of cool air go out, right? So that's the main function. Okay, so that's why in our previous lecture we talked about heat transfer. So this is a very clear application of our previous lecture. And of course, we also mentioned. Now I will skip this part again, so that the key thing here is when we want to, right, this kind of pump this kind of warm air, right, into this kind of air conditioning system, and then produce cool air. So that there are 2 possible ways, as I mentioned. The simplest way is what? Electric fan. But electric fan is okay in some application. But if it like in Hong Kong environment, very hot and humid, the pure electric fan is produce what? Heat convection. Why we mention in heat convection is okay, right? The fan is okay, provides this kind of heat, called forced convection, right? We mentioned in previous lecture, but in some case it's not enough, right? The amount of heat flow through electric fan is not enough. So in this case, we may want to use more effective way to do this kind of heat transfer, right? So that so in this case, we, as I mentioned, we may not only use heat convection. We want to use what? Heat phase change. Huh? Remember we have what? Heat conduction, convection, right? Radiation, and phase change. So that if we use phase change, then that amount of energy to carry will be much more. I mean, right? It's much more efficient to do this kind of heat transfer, right? So that's why here as I show you, typically if you have water, right, in the room temperature, you heat up, right, gradually, for example, in the kitchen, right, and then in this case, the temperature of water gradually increase, right? So that's something, and then this is typical heat transfer, right? Typically they involve what? Heat conduction and convection. And then if it reach some critical temperature, what happened? 100 degrees C, and then you're going to have phase change, right? Phase change, that's a key thing we will learn, right? So here, basically some phase change we mentioned in our previous lecture, why? And then during this kind of heat change, and then the one of important thing you find is the temperature will be constant, remain constant for some period of time. So that why? Because it really try to we absorb a lot of energy, right? And then from liquid to vapor, right? From liquid to vapor. So this is, and this energy is much more compared with this part. Okay, so this is something, and then of course, for this part we call the sensible heat, and this one latent heat. So that's give you something, and again, the amount of energy you can carry for latent heat is much bigger, okay, much bigger than this guy. That's why when we design this air conditioning system or HVAC in general, so that we prefer to have phase change. That is an important thing I want of you to understand. Okay, so that do you understand? So this is something it's important. That's why, as I mentioned, we try to tell you about this kind of basic concept in our previous this kind of lecture, right? And then so that of course quickly can we look at some very common things, so that typically in the kitchen, why when you boil the water, so you have this kind of if this kind of high temperature on this kind of gas stove, right? So then temperature too high, so that in this case we have what? We have a heat radiation, right? And then of course then also heat conduction, convection, right? And then conduction also happens. So and then of course once you reach some critical temperature, again we have a water vapor, right? Liquid turn to water vapor, so the latent heat, right? So this kind of phenomena is very common in your daily life and also in this our environment. Okay, so this is something because heat transfer. That's why we have wind, heat transfer, we have rain, and even typhoon, right? So that is something is quite important. And of course, now we try to describe, as mentioned in the animation, what do you have in this kind of one typical air conditioning system with 4 key components. Why? Why? So that typically we prefer, as mentioned, have some kind of phase change. Why? Evaporator. Basically, this is one which can what? Have phase change from liquid to vapor. Right? So this is basically from liquid to vapor, water vapor. So this is something. And then of course there's another important thing, condenser. Why? It's another phase change happen. Okay, in this thing. So what was this? This basically is from vapor to liquid, condenser. So that this is a two important this kind of thing. So that again both are belong to one particular heat transfer. Why we mentioned phase change, and again they will try to be much more efficient to to carry this kind of energy heat flow. That's why this thing. Right? If you don't have phase change, again if you use electric fan, the amount of energy to carry will be much smaller. So this is something is important. You may want to go back to our previous lecture. I don't still remember. I think also may be interesting, important for you to review. Quickly look at what you have learned in previous lecture about this kind of issue, about that. Let me quickly go. I don't know, do you still remember about that heat convection? Let me try to quickly go back to our previous one. I don't know, do you still remember? We have this kind of heat convection. Why? Heat convection, and then so that if you only have typical single phase flow, maybe airflow, for example, pure electric fan. Why? For fan, pure electric fan. Okay, that's right, electric fan. And then our H relate to what? Heat convection coefficient. Our heat flow Q, why, relate to H and delta T. Why? Temperature difference. So this is something for you to, I think it's important for you to look here. So if you only have air, right, electric fan, and then our H to and HA delta T, right? So that so H will be a little bit small. Okay. That is a forced convection. But if you have phase change, you see, now it's important for you to look at here, this number, this number and this one, boiling condensation. You see? Do you see the difference? This is a typical maybe 39, but this, if you have phase change, like I show you two components. One is condenser, why another is this is a condensation. That's why our condenser in our AC air conditioning system, and then we have evaporator, why from liquid to vapor, why boil, so that means there's another thing. So this is in AC air conditioning. So you can see, if I only have pure electric fan, the amount of heat it can try to carry for cooling about you it's not enough. So that's why in the summer, do you prefer to use electric fan only, or you want to turn on air conditioning system? This slide show you quantitatively the way why you don't like the electric fan, why you want to have this kind of AC with phase change. Do you understand? Any question or comment? That's something is important. Again, do you have any comment about this kind of important about heat transfer, especially convection? Why? For this kind of AC, this is something. That's why we use this kind of one chapter. Why? Describe this kind of basic concept. Is if you don't understand this one, then you will not appreciate. Why? You not appreciate the design. Why? So that's something you can see. We have an order magnitude difference. Do you say? Until the 10, 50. So this is it's almost 100 times. Why? 100 times more. Carried about Q, right? Heat flow rate. So 100 times or more, you can see. So that is something, of course, another thing, drop-wise condensation. That's another kind of important thing. So you see, if you have this kind of condensation in a tube, like we mentioned and then it's on the order of 9,000 to 25,000. If a drop-wise, so maybe if you have many droplet to do condensation, and amount of heat you can carry will be even more, right? This is electric fan. This thing. So that's one. So different kind of heat exchange, why phenomena will have different kind of amount of heat flow we can carry. So that this is something I think it's important for you to refer this one, so that and then it will be more easier for you to appreciate this kind of one we mentioned. Why doing that? If we don't talk about this in quantitative way, and then somehow it's not easy for all of you to appreciate this kind of design. Okay, now I try to really link this particular two key component of any kind of AC. Okay, and then okay, so that's why now I just put down the same thing. Right? We just mentioned this kind of fan, the Q heat flow of fan is much smaller than this kind of AC heat flow. Why? Much more. It's at least 2 order magnitude difference. Okay, so that's why all of you in one prefer air conditioning system in the summer. Okay, so that then of course that's another thing, right? So that we as mentioned, so that when we try to have air conditioning system, so that the key thing here is what's the temperature or humidity or this kind of key parameter we need to control or target this kind of parameter, temperature, humidity, or even thermal comfort we want to achieve. It turns out it's not trivial. Why we mentioned most important parameter is maybe temperature and humidity, but it's not enough. As I mentioned, our our human is very complicated. This kind of thing, our human thermal comfort in general involve, as I mentioned at the time, very complicated. This kind of things in relate to metabolic rate. That means what's metabolic rate? So this relate to if you are sitting, running, jogging, right? Or then this will be different, right? And then another thing is it also depends on your breath, your human breath. Sorry. And then of course it also depends on many parameters. So this is a very complicated heat transfer. So that of course I was mentioning that in the industry they do have this kind of industrial standard or HVAC standard. Why? It typically is a 7-point scale of this kind of human thermal sensation. Why? -3 it's very cold, +3 very hot. Why? So that in general, based on, as I mentioned, this kind of one Professor Fenger in Denmark spent a lot of time doing this kind of human study about more than 1,000 people, right? And then with different condition, temperature, humidity, velocity, air velocity, R is radiant temperature, and metabolic rate and close condition. Okay, so with basically TR is related to this kind of radiant temperature. Okay, so these are the one which can have big impact on our human thermal comfort. Okay, and then of course, typical as I mentioned, our PMV most likely we hope we can be achieved ±0.5, like here. This range will be good, right, method to do the control. Right, in this case, with PPD, I hope still remember what is PPD. Huh? So what is PPD? I hope you still remember, huh? What is PPD? I need to. Did you still remember? So as I mentioned, PMV is average human thermal comfort index. Why? So that in this case, average that means in this case it cannot be represented to everybody. Some percentage of people will be not happy about this kind of human thermal comfort index (PMV). That's why in this case we have this kind of thing. The model not only predict the average human thermal comfort index, but also PPD tell you about how many percentage of people who are not happy, right? Dissatisfied. So that is something. Also, last time we also show you about the online calculator, huh? So that you may want to look at this kind of online calculator to get some more experience about if this is good enough for you, right? You say, last time I already show you about this kind of online calculator, right? So that, for example, today, what do you think? What's PMV for today's temperature? Huh? Can any, maybe it's time? I think maybe I should ask you to quickly do this kind of exercise. What's the PMV? Maybe can you try go to this thing to look at today's PMV? Can you spend like 1 minute? We have a Hong Kong observatory. this kind of thing, and then what is today's PMV? Unfortunately, you see, Hong Kong government, the Hong Kong observer, they don't have this kind of calculator. What's the PMV now? Can you do the kind of simple analysis? I don't think it's meaningful, especially now today is quite hot. So what's PMV? Anyone already calculate? Can you type what's today's PMV now? What is today's PMV now? According to this kind of online website. Anyone can do quick calculation? Not calculate, enter those key parameters from Hong Kong Observatory. So what is the PMV now? Today is quite hot, I would say. Quite hot. 1.59. Okay, good. We have a so that this is something I think worthwhile for all of you to do some exercise. Why 1.59, and then you see, so about 56% of people will not feel very happy. It's warm, right? It's not super hot. So that according to this thing, of course, actually depends on the speed, right? If you look at the Hong Kong Observatory, actually also give you the wind speed. You may want to enter that the wind speed and then get even more. Not only temperature, humidity. I do know that the Hong Kong Observatory to provide this kind of wind speed, right? If you use that one, then it can be a bit better, right? Especially, you see, if you have typhoon, the wind speed is so high, and then you can really, for example, you hit 10, what happened? Oh, outside the, so that there's some limitation. Okay, you see, so that if it has to be too high, so this model, they cannot give you a reasonable result, actually, see. So that if you typhoon, and then they cannot calculate, actually. They cannot this model, PMV model, has some limitation. You see, I try to count 0.5, slide 1, and then 0.9. You see, if 0.9, they already tell you they cannot calculate, because they don't. Why they cannot calculate? Do you say why they cannot calculate this kind of PMV? Any idea? And why? I think because again, this PMV is conducted by this kind of indoor environment, right? With about 1,000 people. They change, as mentioned, change different temperature, humidity, velocity, air velocity. So yeah, very good. So this experiment down, experiment down, they must have some airflow, but the range airflow has some limitation. If you speed too high, and then they don't have experiment data, that's why they cannot give you PMV outside that the air velocity range. Do you understand? So this is tell you some limitation. Do you understand? So that definitely PMV, as I show you, is a model, one type of human thermal model, right? With about 1,000 people, and then air velocity, this V is air velocity, right? So that so in this case, if you look at the website, I show you, so that if you beyond about 1 meter per second, then they cannot give you this kind of data. So this is that means PMV do have certain limitation. Okay, but of course, actually, human thermal comfort index is a very complicated thing. I just tell you here. I just show you. There's index or index. Do you know how many human thermal comfort index existing now up to now? PMV is only one type of human thermal comfort. Do you know how many kind of human thermal comfort indices now like people have invented? Any idea? How many? How many this kind of human thermal comfort index now have been proposed? Any idea? Up to now, how many? One student, Kevin, says 10. No, it's more than 70. There's 70, all kind of very complicated now, different human thermal comfort indexes. And so the PMV is only one there. Okay, it's about 70 plus human thermal comfort. Okay, so it's it's something you are surprised. Why there are so many? Why so many? Why there are so many kind of human thermal comfort indices? Why? Any idea? Because once you involve a human, human sensation is much more complicated. So that some people, some research, for example, some specific kind of study, why? So that it's anything related to human, the kind of sensation is very complicated thing. Why? If you want to have very good, reliable, this kind of quantitative measure is difficult and challenging. So that it depends on the age. Little baby, old man like you, or like a young student like you, may be different. Became a female, male, or depends on Chinese people, different ethnic group, Americans. So actually, it's much more complicated. Okay, so that's why now up to now there's more than 70 human thermal comfort index. Now people have been studied in the past many years. So it's something as non-trivial. Why? It's non-trivial thing. There's another thing as I mentioned. Anyway, so as I told you, it's it depends. Many different this kind of research community also use different kind of this kind of human thermal comfort index. For example, in the military, this kind of area, people in the field, so that they have their own the kind of human thermal index for military application. Why? For typical the kind of people, for example, in the government, Hong Kong government observatory, they also have their a little bit different ways. Do you think? So it's somehow it's complicated, I would say, complicated this kind of topic, and require a lot more. Of course, you can see there's additional SET. SET is another type of, I would say, human thermal comfort index. Now, so that as I told you, there's a long list of different things. So that, but anyway, so as I tell you, it's turned out this topic is non-trivial. It's non-trivial. Okay, I just give you a thing. Of course, as I told you that I do supervise UG student to design smartphone app. So to calculate PMV. Okay, so that's thing, and then actually you can also download the PMV smartphone app. Okay, so that not only on website. So if you look at the this kind of PMV smartphone app, actually there's some people design this kind of PMV human thermal comfort index app, so that you may want to download. Including I know there's some free the kind of smartphone PMV app you may want to download. I think I can give you some website or something to download that kind of PMV smartphone app for you to get more quantitative understanding about this thing, right? IEQ, but Fender. Okay, so that let me give you that this kind of smartphone. So that I tell you this kind of PMV. So you can download. There's some interesting this kind of smartphone app. No, people try to design for free, and then you can try to. I will give you at least more than one thing, including like one UG student work with my PhD on this kind of smartphone, Angel, this kind of PMV app. Okay, so it's something interesting, and for all of you to experience this kind of to have more quantitative understand this kind of topic, right? Because although we give you this kind of let me see. Yeah, this you can find. You can find there's some app you can download, and then I will share you. I'll show you the one developed by my the student 1 or 2 years ago, so that for you to give a try. Okay, so that is something personally I think it's an important topic, but it's not easy topic. Okay. So now again, so the important and difficult part, as I show you, is very complicated, involve metabolism, right? And so if you're sitting, running, jogging, and all different activity at different metabolic rate, closing level, and humidity, ASB, and many things, flow temperature, and all this. So it's a very complicated thing. Okay, yeah, and then of course, now we finally gradually try to describe about this kind of air conditioning history. Again, it's not new. Why? More than 100 years old. We also mentioned last time. The key thing here is one of the most important you may want to understand is this one American, why Mr. Carrier invent the first modern this kind of electrical air conditioning system. Why later on, of course, this company still exists. Okay, so you can, at least in United States, you can find this company, the product. I don't know how about in Hong Kong. Maybe in Hong Kong we don't have too many this kind of air conditioning from this kind of original. But at least I thought in United States, I think these still Hong Kong still have this kind of carriers, the product. Okay, so that and this is a very old company and has history. Let me quickly show you this carrier. So that then after Mr. Carrier who invent the first modern air conditioning system. So I think it's quite useful for you to understand this kind of history, and then you have a more idea how this thing. Right? Of course, in the past many years, so engineers continue to improve this kind of air conditioning system. So do you think there's still something you can improve the air conditioning system? That also a question. Why? We're engineer. Can you come with some new idea about air conditioning system? So that here's a brief history, right? Can you come up with a new idea about this AC? That's something engineer is important thing is we want to come with some new idea, new technology, new design. What do you think? Can you come with some new idea? Or are you happy about the current air conditioning system? Oh, one student too noisy. Definitely, this is one of the issue. Why? So that can we come with some very quiet air conditioning system? Very good. We have one student mentioned how to solve the problem of too noisy. That's another question. Noisy because we have one important component we mentioned in the animation, because we have compressor. Why is noisy? Remember we show you this one. We have this kind of thing, right? Let me show you this animation. We have this kind of compressor. Compressor will generate a lot of noise actually. Let me show you. So this design is not new. It's okay, but it's not perfect. Compressor, this guy can generate a lot of noise. Huh? Very good. We have student mentioned, why? Chun Ying mentioned that is any way we don't use this kind of freon or something which is harmful. It's not good, right? Actually, it's bad for global warming. So, what do you think? Do you have any other solution? I tell you, the answer is yes. There's also room to come up with a new idea. For example, I don't know if you heard about thermoelectric. Thermoelectric, this kind of cooler. Do you have ever heard of this kind of? Sometimes they call semiconductor device. So basically, these are the one can be useful to replace this kind of traditional air conditioning system. Okay, I'm here, thermoelectric cooler. Okay, so that this one is again solid state. Sometimes semiconductor device. Okay, and so people use this one, maybe try to cool, maybe cool the kind of maybe food, right? There's some portable, the kind of a cooling system preserve the food. So basically, you can find thermal is a cooling device, and so that of course the amount of heat to carry may not be large enough. That's another thing. So that the thermoelectric cooler is one possible way to do this thing, and then there's no noise. There's no noise at all based on this kind of Peltier effect. But unfortunately, the amount of heat to carry may not be good enough compared with traditional air conditioning system. That's something I tell you. Unfortunately, we have no perfect this kind of system. So that's why still this kind of design still now dominant in our commercial, this kind of commercial world. So that this kind of thermal still they have some useful thing. For example, how you can cool your laptop computer. So actually, I also bought this kind of thermoelectric device to cool my laptop computer. Okay, and so this is something I tell you. In some case, or you do combination of electric fan with thermoelectric cooling. Why? So that this is possible. So that if you look at those kind of company, especially next to Hong Kong, you can find those kind of thermoelectric cooler for laptop computer. It's something important actually, because as I show you that we have a lot more this kind of advanced CPU for computer, right? So in this case, I told you that you can, if we go to this kind of Alibaba website, and you can find those kind of cooling system for it's not for the building, but because amount of heat is not good enough, so that at this moment. But still, I do think if engineer, you can really design better thing. Maybe in the near future, you can come with this kind of thermoelectric, this kind of device with electric fan, right? So that in this case, I think it's possible, but unfortunately, the amount of heat to carry can be good enough for computer, but not our building, not level, and it's still not enough. That means require additional research from you or something to see if possible you can really come with a new design of which is much better and no noise. Okay, so that today I think it's good to get some additional comment from our students, so that you say I do say if you keep talking without have some discussion, then you may too boring. Okay, so now we try to look at this additional thing, and again, of course, besides air conditioning, of course, we have other things. Now it's too hot now. Maybe you prefer to buy some Coca-Cola, some drink, right? So in this case, typically for this kind of refrigeration, we most likely will also have this kind of heat transfer, right, to cool down all the food inside this kind of refrigerator. Okay, and in general, I think here let me just quickly give you this kind of more detailed description about this kind of thing. Again, according to our first video, right, with 4 key components, right, 1, 2, 3, 4, right, and then we try to describe a little bit more detail for each component. And then first, basically, even air conditioning system or refrigeration system, they all have the kind of 4 key component. Okay, and then compressor, as I show you, this is one of the component who generate a lot of noise, right? Because you continue to do the mechanical work and then compress the air, right? So that this can create some, of course, efficiently to compress, doing that, compress this kind of thing, so that the from you can see compress into high pressure vapor. So this is something important. And then of course, condenser, we also mentioned. Condenser is what? Basically condensation. We mentioned in why this is a one special key component. You can cause some of liquid has some kind of condensation, right? And then so that this is something quite important, right? And then another important thing is we call the metering device. What's this? That means once we have it's some important this device which can really try to do regulation of this kind of a very complicated heat transfer, right? Basically, we have a heat convection, forced convection flow, right? And then so that in between evaporator and condenser, right? So that in this case, why we want to do this kind of regulation? Basically, it's a regulation of this kind of thing, right? So that what do you think? Why this is important? So the most important concept here is they will try to control certain delta T, the temperature. Maybe one temperature relate to evaporator, and then another what? Evaporator and condenser. Evaporate, and then so this machine, this device basically try to control delta T. Okay, or they call superheat. So that this thing is something quite important. And typically, I will show you one of most commonly used this kind of valve is what called the thermostatic expansion valve. So I think it would be useful for all of you to look at this video so that you can have certain more idea about how this works. Let me show you.
Hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be looking inside one of these, the thermal expansion valve by Danfoss. Coming up, where do we find them, what are they used for, and then we'll cut one open and discuss the internal components and how they work. If you want to get the most out of any thermal expansion valve, then you should definitely check out the TXV Superheat Tuner. It's a free mobile app available from Danfoss, who have kindly sponsored this video. You can use it to optimize the energy efficiency of a cooling system in just 15 minutes, which saves money on energy costs. You can download it for free using the link in the video description below. So where do we find the expansion valve? Expansion valves sit between the condenser and the evaporator in a refrigeration cycle. In this model, which is a T2 thermal expansion valve, we have the main body, which is made from brass. On the body, we have the refrigerant inlet at the bottom of the valve, then the refrigerant outlet at the side, and on the other side we have a cap which can be removed. Under that cap is a screw which is used to manually adjust the superheat. We'll see how that works later on in this video. On the top we have this large head called the power head. There's also a coil of very thin tubing known as the capillary tube, and there is a large bulb at the end of it known as the sensing bulb. These are all made from stainless steel. The coil is stretched out so that the bulb sits at the exit of the evaporator to sense the superheat. We have previously covered in great detail how thermal expansion valves and electronic expansion valves work, as well as the different types of expansion valves used on chillers. Do check those out, links are in the video description below. What are expansion valves used for? Expansion valves control the flow of refrigerant into the evaporator in response to the cooling load. They measure the superheat at the outlet and react to this, increasing or decreasing the amount of refrigerant flowing into the evaporator to try and maintain a constant superheat. This also ensures that the refrigerant is boiling off and it will leave the evaporator as a slightly superheated vapor and prevent liquid refrigerant entering the compressor. Liquids cannot be compressed, so if they enter the compressor, this can cause severe damage and even destroy it. The bulb is filled with a refrigerant which is kept completely separate to the refrigerant in the rest of the system. These two refrigerants never meet or mix, they are always separated. The superheat boils the refrigerant inside the bulb, and as it boils, it creates pressure. The pressure travels along the hollow capillary tube and into the power head. The power head controls the flow of refrigerant, and we'll see inside that later in this video. We place a removable cartridge inside the inlet of the expansion valve. This has an orifice which works with the valve to control the flow of refrigerant. There are different sized ones depending on the cooling capacity and the refrigerant being used. Okay, enough about that, let's cut it open and look inside. I'll just put the valve into a bench vise to keep it steady while I cut it open. Because of the delicate parts inside, I'm going to use a hacksaw to cut this one open. It does take a little longer, but the angle grinder could rip apart the internals and I want to be able to show you these parts. Okay, that's the first cut done. I'll just rotate that in the vise to cut the other side open. Again, I'm just going to use the hacksaw here to cut through it. That's pretty much cut now. I'll just use a chisel to snap the last little bit inside. And there we go. So let's have a closer look inside. So we have the main body which holds everything together. We have the refrigerant inlet coming in from the bottom of the main body in this vertical pipe, and then the refrigerant outlet on this horizontal pipe. So the refrigerant comes from the condenser and enters the valve body via the inlet. It enters at a high pressure, medium temperature saturated liquid. It then passes through the valve body, and when it leaves, it exits the valve through the outlet and will now be a low pressure, low temperature liquid vapor mixture. So what's causing the change in pressure, temperature, phase and also controlling the flow of refrigerant? Well, we can see this small pin here. This is connected to the diaphragm up in the power head. The diaphragm is a thin sheet of flexible metal. As the diaphragm moves up and down, it causes the pin to move up and down also. Underneath the diaphragm, we have a spring which is pushing up against the diaphragm. We can use this to adjust the superheat, and we'll look at that a bit later in this video. Above the diaphragm, we have this empty chamber which is connected to the capillary tube and then the sensing bulb. The chamber, the capillary tube and the bulb are all hollow. I'll just cut through the sensing bulb using an angle grinder to show you the inside. As you can see, it's just an empty cylinder which is usually filled with some refrigerant. The refrigerant in the bulb and capillary are completely separated from the main refrigerant which flows in the system. This isolated refrigerant only moves between the bulb, the capillary tube, and the top of the diaphragm. The sensing bulb sits at the outlet of the evaporator. As the cooling load on the evaporator increases, the superheat increases at the evaporator outlet. Because the sensing bulb is in direct contact with the pipe at the evaporator outlet, the thermal energy transfers and causes the refrigerant inside the sensing bulb to expand and boil. Because the sensing bulb, capillary tube, and the chamber are all hollow and are a sealed system, as the refrigerant expands and boils, it causes the pressure inside to increase. This pressure travels along the capillary tube and makes its way to the chamber above the diaphragm. As the pressure increases, it pushes down on the diaphragm and this pushes down on the pin. The pin controls how much refrigerant can flow, but to do that we need one more part. Inside the inlet of the valve we place an orifice assembly. Inside is a small strainer which protects the valve from blockages. Then there's a small orifice or hole which is blocked by a spring-loaded stopper. Our pin in the main valve pushes down on this stopper to open the valve. The further the stopper is pushed down, the more refrigerant can flow. As the cooling load increases on the evaporator, the superheat increases at the outlet. The sensing bulb at the outlet detects this and the refrigerant inside boils, causing an increase in pressure along the capillary tube. This pressure pushes the diaphragm down and that pushes the pin down, which opens the valve and lets more refrigerant flow. As more refrigerant flows, the superheat decreases and so the pressure in the sensing bulb and capillary tube decreases, which means there's less pressure pushing the diaphragm down. The spring then pushes the diaphragm back up, which causes the pin to move up, and as the pin rises, the spring-loaded stopper begins to close the orifice, which reduces the amount of refrigerant that can flow. This repeats constantly and stabilizes the valve to ensure the correct amount of refrigerant can flow. We mentioned earlier about adjusting the superheat control. Well, this plug on the side is threaded internally, and if we rotate this, we can move the slider up or down depending on which way you rotate it. As the slider moves up and down, it changes how much force the spring is applying to the underside of the diaphragm, which changes the sensitivity of the device and allows you to therefore tune the expansion valve and adjust the superheat. I just want to remind you that you can download the TXV Superheat Tuner app.
Okay, so this is, I think, one of the most interesting and clear way to describe how this works, because if you only look at this video, all these pictures, I think it's very difficult for you to understand this kind of dynamic way how this works, right? So again, what can you make a simple summary about how this works now? What do you think? When you look at this thing, so that again, the key thing is this kind of valve is trying to control the delta T. They call superheat with some special temperature sensor, right? Temperature that is something quite unique and important, right? And they call the sensing bulb. That is I would say is like kind of special, interesting temperature sensor, but it's a mechanical way to do this kind of thing. The key thing here is they have certain kind of sensing bulb here. And then in this case, they try to make sure they can sense certain temperature, then try to provide a feedback to this kind of thing to adjust this kind of flow, right? And in this case, they can really try to maintain proper this kind of flow rate and things, so that this is quite important, right? Again, the key thing here is they want to make sure that this is a one direction flow. I think the bottom line is if they provide kind of a one directional flow, because in the upstream and downstream of this valve, so what different? One's liquid, right? And here it become mixture of this kind of here flow. Here is pure liquid, and now one's here vapor. Do you see? The vapor actually is not pure. It's a compact two-phase flow, I would say, with some combination of the liquid and vapor. So this is quite important for you to understand. So once you have this kind of evaporation wise. So it's not very ideally all this liquid suddenly become vapor. So there's certain transition. It's a mixture of this kind of liquid and vapor. So that this one actually will prevent only like this one thing here. So we'll not let this kind of vapor to go back to upstream here. Okay, so this is something quite, because the bottom line is if this kind of vapor go here and then enter the compressor, then what happened? Compressor can fail. So this is very critical. Why? Component is, if you don't understand about very complicated this kind of phase change, why? And in that kind of thing, then I think it's difficult for all of you to really understand about the reason why we need to have this kind of special device. Is that I told you this is somehow it's non-trivial, I would say, for you. So the key thing here is with this kind of valve, so that you can really have better control about very complicated two-phase flow. Why? There's some mixture of liquid and vapor here. So this can create very complex thing. And so this and another important thing, once you mixture of liquid and vapor and what happens? Actually, you produce some very complicated, I would say, this thing. That means most likely as function of time and then the pressure of this kind of thing, and then you fluctuate. Okay, so this is a mixture of liquid and the vapor, and then it's very not stable here, fluctuation, and then so that this is not good. Now, so this is one of quite important for all of you to understand about this kind of thing. Although this slide shows some very basic thing, but hopefully you understand. With look at this video, it's much easier for you to understand here. And then again, so that now we look at one of a very important component for every AC. So again, so this is evaporator, right? I mentioned, so that again, the more important thing is they produce this kind of effective heat exchange. Why? So the most important thing, they have some special heat exchange, I would say. Okay, and then so that by doing this kind of phase change, why? Boiling, and then there's some effective heat exchange, so that this is important component. Why? Phase exchange. Why? In this kind of special evaporator, and so that is something quite important for all of you to understand the basic things. Why? And then of course, there's another kind of important thing. Condenser is same thing I mentioned. Condenser is another important heat exchanger. Why? With phase change, but from vapor to liquid, right? So this is thing, and then of course I mentioned there's different kind of this kind of condenser. One is air cool condenser. Why? And then you can use small flame. And air cool, what does it mean? Only single phase or the flow, so that the amount of heat can carry would be smaller compared with this kind of evaporate. That's why here, this has some phase exchange. So the amount of heat can carry would be much more efficiency, right? Doing that. So this is I will try to show here. Basically, this one is a single phase. This kind of heat exchange, right? Single phase heat exchange, right? And with air, so that if you look at previous lecture when I mentioned H, right? Heat convection coefficient will be not two, but here for this one, basically we have two phase. That means a mixture of liquid and vapor. two-phase heat exchange. Why? So that this can carry a lot more this kind of a heat flow. Okay, so that is something I think both of them are useful. Why? If you have very large building, and then it will be much more efficient. Why? Okay, and of course, if it's small, for example, at home you have a wall mount air conditioner, we just show in the first video, so that is okay. So that the both has been used in real product. Why? Okay, here I show you sometimes also have this kind of huge. You see, this is the air cooled the system. Why? Condenser system 550 tons. Look at this human here. So it's a huge this kind of machine. Okay, and then so of course that's the reason. Is that if you want to have a carry much heat flow, and then it turns out we're much larger. Okay, we have some students. One student mentioned about single phase remain liquid or air. One student asked about that thing. Here I show you about this kind of thing. Air cool condenser, right? It's single phase, right? It's kind of it's not liquid. But of course, this is something as I mentioned that were different design. Some of design they have a phase change. Why? It's a phase change evaporation. Why? Okay, and any other question? Again, so that both design has been used in real product, okay, in the industry. But on the other hand, this kind of this kind of condenser, I show you the amount of heat to carry a bit much larger. We just look at that previous video, previous lecture again. I need to let you to understand why the importance of that table. Then you will be easy understand of why we engineer need to use this kind of more complicated design, because it carry a lot more energy here. Why? You have this kind of droplet-wise condensation. Why? You see, your H heat convection coefficient will be much larger. Why? Can do a single phase forced convection. This can clearly show you the big difference between these two different designs. Okay. Okay, so that this I don't know, do you have any other question? Okay, let me quickly show. So that basically this you see this is quite common in typical this kind of air conditioner in Hong Kong, I say. Why? And so that in this case, again, you have this kind of compensation, right? And then so that in this case, you can generate much better heat exchange, right, for cooling. But again, there's no perfect for engineering this kind of design. There's no perfect. What's the problem of this design? It turns out once you have this kind of droplet, and then this can carry, you can see, contaminated by this kind of bacteria or viruses. For example, now we're COVID-19. So that if the virus, COVID-19 virus, suspend and then trap in this kind of droplet, you may have problem. Do you understand the issue? This is not new, actually. There's many this kind of central air system that will suffer about this kind of contamination with bacteria, especially this particular one. I'm here. Legionnaire bacteria. Actually, about 2 years ago, one MTR station like Troy Home, they do have this problem. This kind of bacteria exists in typical central air conditioning system. It's very common. It's not a thing, right? Of course, COVID-19 is another possible way, right? So if you have so many people got this kind of COVID-19 virus, and then maybe some of this virus will spread to this kind of central air conditioning system. This may be very bad for all of you. Okay, so that anyway, I just tell you this is something it's still a big issue in terms of building engineering, right? So that it's not it's people still need to solve this problem. Now let me quickly show you Hong Kong government's
Legionnaires' disease is caused by a type of bacteria called Legionella. Clinical features include fever, dry cough, shortness of breath, tiredness, headache, and muscle pain. In severe cases, respiratory failure and even death may occur. Persons aged over 50 years, those with weakened immunity and chronic illnesses such as cancer, diabetes mellitus, chronic lung or kidney disease, those taking corticosteroids or drugs that suppress body immunity are at higher risk. Legionella bacteria are found in sources of water. A person can develop Legionnaire's disease by breathing in contaminated droplets and mist. To prevent the infection, one should avoid smoking and alcohol drinking, as well as to prevent bacterial growth in water.
In this kind of cooling tower.
Remove strainers in water taps and shower heads quarterly for cleaning. Drain for at least 1 minute the infrequently used water outlets and stagnant points of pipework weekly or before use. Persons who need to use home respiratory devices should seek and follow doctor's advice. Clean and maintain the device according to manufacturer's instruction. After cleansing or disinfection, rinse the device with sterile water, cooled freshly boiled water, or water filtered with 0.2 micrometer filters. Wipe all surface dry. Ensure no stagnant water. Change the water inside the device daily by first emptying the water tank, then wiping the surface, and finally adding water. Persons with weakened immunity when drinking, toothbrushing, and mouth rinsing should use sterile water or cooled freshly boiled water. Avoid using humidifiers or mist-generating equipment. For more details, please visit website of the...
Okay, so this give you important message for all of you, right? In your daily life, not only you see this kind of cooling tower, right? The condenser have this kind of problem, but even at home, you need to be careful about this kind of possible contamination with this kind of bacteria. Of course, now it's COVID-19 virus. Okay, this is something important for all of you, right? And then, of course, one more this kind of thing happened in Hong Kong is Hong Kong actually right next to seawater, right, surrounded by all these seas, so that in this case, can we leverage kind of seawater for cooling? Why? How to do that? So this is quite special for Hong Kong actually. So that again, important thing. Why seawater is good? Why seawater is good? Because seawater actually is a large thermal mass, right? Doing that, so that then in this case, remember this kind of heat capacity of this kind of big thermal mass. So that in this case, most likely, if you pump this kind of warm water to the seawater, most likely it will not change the temperature of seawater. Right? So then in case seawater can be seen at a constant this kind of temperature, the big reservoir, right? So that in this case, it can really avoid to use the kind of energy, right, for this kind of a traditional air conditioning system. So here I show you what's a typical temperature, right, we can explore to use the kind of seawater for cooling, right, for building. So you can see, typically the temperature of this kind of seawater depends on depth. So that here is show you from 0 to 1,000 meters, the temperature can really drop from room temperature to almost to very low, 4 to 5 degrees C. So do you think so? This is a quite important thing. So you can save maybe 90% of the energy. So that it's good for those building next to this kind of seawater and ocean, right? Like Hong Kong or UST. Right? What do you think? Do we have this one in our UST? It turns out, okay, this kind of thing again, so that this require this kind of sophisticated, this kind of cooling system design. Okay, one student say yes, actually, our UST do have this kind of seawater cooling system. Okay, so that yes, our HU actually has this kind of water cooling system. Okay, so that's something you may want to look at carefully about this kind of our UST, this kind of system. Okay, to any question? Okay, again, I still recommend if you have I provide a kind of free of charge trial session to try the Facebook VR, so that if you never use it one, you can try to sign up on this kind of a doodle, and then so that again it's free. But I do think it would be interesting and useful for all of you to experience this kind of VR, AR, or something. I do believe will be interesting and useful for all of you.